Okay, welcome back for the second lecture. Let's make a start. So an informal warning first, then I have also a slide for a formal warning. I certainly have packed way too much content into today's lecture. Therefore, no break in the middle of the lecture. We just keep going. So I hope you have caffeinated enough. I hope also you have eaten enough, as I will eat through the lunch break as well. No, I'm joking. I will try to stop eventually at some point. The second warning is I apologize if I start to cough every now and then. It's a 1 month long cough spree or something like that. So yeah, please tolerate that. Okay, let's make a start. So this lecture follows very nicely from the one of Suzanne, because she has already introduced a few of the topics we are going to talk a bit more in depth today. And she has already made some points, more broad points, that I hope I will have time at the end of the lecture to actually go back to them, reconnect to them, and provide a slightly different view to that. Okay, so the focus of this lecture is generative information retrieval. And what do I mean with generative information retrieval is the use of sequence-to-sequence language model to perform IR tasks. And I was having a chat today after breakfast with Sean, and we were arguing of how good of a definition this is. And you know what we mean is language models that we will call large language models for simplifying, but they do not include encoder-only models, so don't include BERT. It only includes encoder-decoder and decoder-only models, but not all of them. We don't really care of GPT-1, right? We only care of this more modern one. Almost we only care about instruction-tuned large language models. But even that is not exactly correct. Sometimes we can look at and use non-instruction-tuned versions of these large language models. So it's a bit hard to pin down exactly the boundary of what I'm meaning when I say generative IR. But you know, keep going with me. Just make sure that when I say LLM, you do not think about BERT style, encoder only, but you think about these encoder-decoder or decoder-only models. Okay, so there are 3 directions that I'm going to talk about today about generative IR. One is using these large language model for retrieval and for ranking by prompting them. And I put prompting here with you. I put it slightly in a quote because we will see when we talk about them, there are different level of prompting, from very, very simplistic prompting to really prompt engineering type of approaches. Then we will talk about retrieval augmented generation, which Suzanne has already introduced. And then we will talk about model-based IR, so differential search index as an example, which also Suzanne has mentioned at the end of our talk. Now, when other people talk about generative IR, there are differing views of what exactly we mean with generative IR. Some people really think just about model-based IR as being generative IR. Other people take a more broader approach. So there is a bit of disagreement in the community around that. But follow the flow here. You know, stick with this definition. These are the 3 topics I really want to talk to you today. So I say that I had a slide, an official slide on disclaimer. Here it is. So I will have no time. I'm sure of that. I will have no time to cover all the slides. So the slides are made available publicly, and you can use them to go to see things a bit more in detail that I've skipped, and perhaps slides that I ran through or something like that. And in the slides, I always try to give you some pointers to further reading or the reference to the actual paper. So you should go and read that. Don't think this lecture as being a comprehensive overview of all methods that there are in the space. Cannot be done in an hour and a half. I only will provide you a few examples. And these examples I provide you, you can distinguish them more or less in two types. Some are fundamental work, right? Well-recognized work, fundamental work that really you should rely upon. And then there are instead some other work that are really recent works. There are a couple of papers that I'm going to talk about that are from July 1st this year, so 2 days ago, 3 days ago. So these, I put preference on these more recent work because the field is moving so fast that I think it's really, it does make sense speaking about the more fresh work. However, be careful that these are not necessarily perfect works, okay? Most of them are not peer-reviewed. Some of them do have mistakes or things like that. So, you know, always go back to the paper, read it yourself, and judge by yourself whether that's a paper you would trust or that's a paper that has a nice idea, a nice intuition, but all the experimentation is not completely wrong, and you should relook at that more carefully. And I will talk about methods most of the time in a simplified or restricted or high-level manner to try to give you the gist of the methods, right? And you know, sometimes my lingo will be sloppy, sometimes my explanation will be slightly sloppy to try to simplify things because of time restriction. But so always, you know, don't trust what I'm telling you. Go and read the actual paper if you're interested in that, right? So I'll give you the gist, then go down to read the paper. Good. So I said that I'm going to talk about 3 directions. Let me slightly correct that. I will not spend equal amount of time across the 3 directions. In particular, I will not talk much about the ESSIR. So I will not talk much about model-based IR. And that's because there has been a tutorial that is called Generative IR, Recent Advances Generative Information Retrieval, been a tutorial organized by a few people, including Martin from Amsterdam, that has run now several times in the IR community. I believe it started in SIG-IR last year. It has been at ESSIR, it has been at DAB. This is the screenshot from DAB. It will be a SIG-IR in a week time, a week and a half time. It's a great tutorial. It's really good. So if you want really to go deeper about the ESSIR, go to that tutorial. It's really well done. I will just give you very brief gist. If I make it in time, I will give you a gist about the ESSIR, and then I will point out maybe very lightly a couple of things they do not touch upon in the tutorial. They do not touch deeply upon in the tutorial. Also, don't get me wrong, there are great resources there for the other 2 areas I'm talking about. However, they are not super easily accessible. So a very good event that happened a couple of weeks ago was the BI conference in Beijing. Amazing. That was a 2 days full on LLMs and LLMs for information access, search and so on. There was a lot of things that they talk about that I'm touching on today. The only issue is that it is in Chinese. So not everybody speaks Chinese, or not everybody can do like me that takes their Chinese PhD student and enslaves them to look at them and translate for you what they say. But I believe they have released, I know they have released their videos of the talks on their website. You need WeChat to register and to access them. And I believe, I haven't seen it, but I believe they have automatic AI captioning turned on. So even if you're not Chinese, you might be able to get the gist, if AI works, of what it has been said. So I suggest, if you're interested in this area, I suggest that you try to get access to that content as well. Okay, let's start talking about prompting large language models for ranking and retrieval. So let's start from the key intuition. What we are trying to do here is asking ourselves, can we ask the large language model to retrieve documents for us. That is, to generate a representation of our documents, of our queries, that then we can use to do matching, right? So for example, can we say to ChatGPT, here is a document, create for me an embedding, and here is a query, create for me an embedding, and then I use in a product design similarity to match these two embeddings and then retrieve documents. So that's what we are trying to do here. We are trying to use the prompt that we give to this large language model, put in the prompt the document, the query, more documents, and get a representation out there. And then use that representation for doing retrieval. So that's the retrieve task. The ranking task, the intuition there is, can we ask the large language model to tell us the relevance of a document to a query? So in the retrieve task, we are really going to use this by-encoder architecture that you heard yesterday from Sean. And instead in the ranking task, we are really using this cross-encoder type of architecture, right? We are giving the query and the document at the same time to the LLM. And we ask it, can you tell us the relevance? And then we can use that indication of relevance or relative relevance of a set of documents to the query to then rank the documents. Okay, so again, we have our prompt, right? We put in the passage, the document, we put in the query, and we ask the LLM, does the passage answer the query? We send that to the LLM, and we get yes, no, for example. And we decide to rank documents according to that yes and no. Okay, so in at a high level, the idea is to devise prompts or devise instructions to tell the LLM how to perform this task effectively. So let's first focus and get a bit more into that retrieve aspect. So the plan here is that I'm going to talk about large language model for dense by encoding. So you should be familiar with that, with what I mean with dense by encoding since yesterday. I will look at leveraging LLMs for data generation to do this dense by encoding then. So again, connecting to what Suzanne said before around data augmentation using LLMs for data augmentation. And then I'm going to move into talk about really using these LLMs not just to do data augmentation, but to do as a backbone to the actual encoding process. And then I will talk about using these LLMs as representation creators, but not just for dense representation, but also for sparse representation, and therefore dense and sparse hybrid representation. Okay, and I will talk about this in a zero-shot manner. And zero-shot is one of these terms that I use in a very sloppy way, right? Zero-shot. If you hear zero-shot, you would interpret, oh, there's not training at all, and that's true. When you think, okay, I take the large language model, I don't do any more training, I use it directly on my task, I get back the answer. I haven't trained the large language model for my task. However, the large language model was pre-trained, right? And it might be pre-trained on the task that you actually are doing, just you didn't know about that because you didn't train the large language model yourself. So zero-shot, meaning there is no further training you have done yourself. Good. So let's start with the talking about dense representations. So the first work I want to talk about is the Gecko embeddings. That's from DeepMind. So being a Google paper, there are a number of details that are not said or unclear. So in particular, it's unclear to me what's the LLM architecture they used. Did they use encoder-decoder model, a decoder-only model? They actually use maybe a encoder-only model. It's unclear. It's most likely, though, that they are using the Matryoshka embedding technique. The Matryoshka embedding technique is where they are training a large network, and so therefore a large representation, but then they have multiple objectives, and they can slice the representation with smaller embedding sizes, right? So that you can have, you know how you have a Llama 7B and Llama 27B version, right? Instead of creating them separately, you can create one at the same time, but slice it into smaller chunks, and medium chunks and large chunks. And that's a much more effective and efficient way of creating these embeddings. But there they use LLMs in the way they train the encoder. In particular, what they do is they use the LLM to generate a few shot examples. So they generate a synthetic data set, right? They call it FRET, and they use that for knowledge distillation. So they take the data set they created and they then use the data set to train their encoder. And to create the data set, they do two tasks, two main tasks. One is creation of queries. Given a passage, create queries. And that's they ensure diversity in the queries that they create for that passage. And the other is positive and negative mining. So let's zoom into these two tasks. So for the query task generation, they take a document and they say, okay, prompt, they give the prompt to the LLM and they say, given a query for this, given this query, find a passage that has the answer to the query. So in this way, they do question answering, or given a query, find a passage that allows you to check whether the query is true or not. And so they do task factor checking. And then they use also the LLMs to do positive and negative mining. So you know that in common approaches for training your encoders, you do have positive and negative documents because we had this gift and this nightmare of having a mass Marco. We all believe that we should that we only have one positive document and we have no negative documents. We need to invent a negative document because that's how a mass mark is done. And so there's been a lot of work on mining negative documents. And what they've done is let's use the large language model to create for us these positive and negative documents. So they observe that the generated query focus on particular aspects of the original passages. We shouldn't use that original passage as a positive and related passages as positive because the aspects are different. And so what they do is they sample new positive and negative documents by using an initial by encoder model trained with the seed passage to retrieve pairs of top passages. Then they use an LLM to rank these passages. Then they use multiple LLMs, they fuse them together, so they do an assemble, and then they take the top ranked passages as positive and others as negative. Okay, so that was Gecko. So in Gecko, the LLM wasn't the backbone. It was used for data augmentation to create synthetic data. Let's move to a different model, E5. So E5, there is an original version of E5 that is BERT-based, but then there is a newer version of E5 where they replaced the BERT backbone with Mistral. So that's a GPT style, so the coder only backbone. And they use this E5 Mistral uses large language models in two ways. One is similar to Gecko. They do synthetic data generation. In there, they prompt an LLM. They use GPT-4 to brainstorm a list of potential retrieval tasks. Then they generate for each retrieval task, they generate a query, a positive document, and a hard negative document. So here is an example in the figure of how they do that, the prompts that they use to GPT-4 to create that synthetic data. But then they actually go and replace, as I mentioned, they replace the backbone and they use the LLM in the backbone. And so what they do there, they take the query, they modify the query by appending an instruction, and the instruction is the task definition. So they define the task they want to do, find relevant documents, or find documents that support this evidence, or find documents that have counter argument to this evidence. So that's the task definition, and then they append the query to that. That's the modification they do to the query, and then they do a second thing, that is they append an end of string token, so the US token, to the end of the query and to the end of the document. Then they feed either this new query or the new document with the end of string. They feed it into the LLM, and then they cut the last layer of the LLM. They look at the last hidden layer, and they take the last hidden layer of that EOS token, right? And they use that as the representation of the query or the representation of the document. Okay. And then they do the embedding. Then they train this embedding, right, by doing the usual contrastive training. Okay, so the training itself, I mentioned they do contrastive training. They do contrasting training in two ways. So that's the broader E5 methods. They do some pre-training where they use weekly supervised data from filtered text pairs. Practically, they take a document, they take 2 consecutive sentences of the document, they split it into 2 different documents, 2 passages, right? And they say, if the query was the first passage, you should retrieve the second passage, something like that, right? And so this is a very weak supervision, right? But you have a massive amount of this type of data. You can go and warm up your model. And then they do contrastive fine-tuning on actual data with actual labels. There could be labels that have been synthetically generated. So this label that I talked about before, right, that the LLM generates for you, or can be labels that have been given by humans, so like the labels in a mass marker. Okay. They also have several versions of the model. The full version of the model doesn't only use supervised mass marker labels. They use further 18 data sets with labels to train even more, even better. But what they found is that unlike with the E5 based on BERT, where that contrastive pre-training was actually quite good, for the new backbone, the new LLM-based backbone, the contrastive pre-training has very negligible impact on the quality of the model. And so there, what you start observing here from this model is that when you're moving away from the previous generation encoder-only model, and you're moving into these auto-regressively trained LLMs, right? You are starting getting a different power in the representation they can create, and you need to do less tricks to get them to perform well, right? So in particular, that you don't need to do that pre-training anymore, that contrastive pre-training anymore. And you only need to do some type of fine-tuning here in E5, and you will see in a couple of slides, maybe you even don't need that fine-tuning at all. So again, what E5 is showing us with respect to the previous generation E5 based on BERT, or with respect to other models, is that this move to these larger and auto-regressively trained LLMs are giving us access to more powerful models that require less training from our side to make effective for the task of retrieval. Okay, so another model I want to talk about is LLM2Vec. The idea there is, again, to use the LLM as your backbone, but they do it not specific to one LLM. They devise a technique that can be applied to any decoder-only LLM. And what they do is they do 3 steps. They modify the architecture by enabling the bidirectional attention. So I think from the first day, you would have learned that these decoder-only language models don't have bidirectional attention, right? They switch it on instead. Then they do next token prediction to make the bidirectional attention work, right? And then they do some contrastive learning. The contrastive learning can either be done unsupervisedly, or optionally, you can even do it supervisedly, so with labels. So let's go through each of the steps, each of the first 3 steps. So they enable bidirectional attention. What that means is that now each token has access to every token in the sequence, right? And therefore you have a bidirectional LLM in all effect. But just enabling that is not good, right? Because the decoder only wasn't trained to attend to future tokens, right? It was trained to only attend a previous tokens. So that's why you need to do a bit of retraining, right? Or do a bit of mask next token prediction to make that self-attention work, really. So you want to get the model now aware of the bidirectional attention function, so you want it to attend to the future tokens as well. And so they do next token prediction to do that. Okay. And lastly, they do unsupervised contrastive loss. So here again is a bit of a trickery. You take a passage and you pass it twice into the model, and then you want to predict that they are the same passage, right? And you use that to train the model. When you pass the passages, each time you do some type of dropout, okay, so that they are not identical, but then you want the representation to be very, very close. Good. So then for obtaining representation, if you remember, the previous model we talked about was injecting a token, the end of sentence token, then we use the embedding of the end of sentence token. The LLM2Vec folks, they've used that as a possibility, or they say that, you know what, we take the embeddings of every token and we do mean pooling, or they tried, let's take the embedding of every token and let's do a weighted mean pooling. And what they found is that in that case, mean pooling was working best. So they are considering all the token embeddings. And okay, the effectiveness is not as good as E5, but certainly it has less training done. The last work I want to talk about in this section is an attempt to try to reduce to the minimum the further training that we need to do to create this representation. So all previous methods, all these methods we talked about, they do have a step of contrastive training, whether it's supervised, whether it's unsupervised, but you still need to do that, which means you still are spending money, whether it's your university money or whether it's your AWS account, you still are using money to train that encoder. And so we can ask then ourselves a question. Can we engineer the prompt of the LLM to obtain an effective representation without the need to do this contrastive fine-tuning? And that's what prompt reps does. So these are a zero-shot, right, again in quotes, approach to generate representations with these large language models. So the idea at a high level is you prompt the LLM to represent a given text, say a document, and you say, oh, represent it only with one word. So you look at the prompt here, you say you have an AI system that can understand your language. Here is the passage. Use one word to represent the passage in a given task. Make sure the word is lowercase. You say the word is, and then you get it to represent one, to generate just one word for that passage. And then what you do is you cut the last layer of your LLM, and for the last token, your prompt, that's a quote, right? And then you use the logics that are associated to that last hidden layer to obtain a sparse representation for your LLM. And you do the same. You use that last token hidden layer to obtain a dense representation. And now you have two representations for your passage, a dense and a sparse one, and you can do whatever you like with two representation. Sean yesterday mentioned very briefly that these hybrid approaches, where you just do a quick ensemble of the two representation, you do an interpolation, right? And that's the whole idea. So very simple idea. It's a very simple idea, but it actually works, surprisingly works. So the experiments that we have run show that these representation independently, so your dense representation, your sparse representation, they are okay, but not particularly good. But when you manage to combine the two representation together, then you actually get some interesting results. And this is without any further contrastive training. I say that you, in the prompt that you're using prompt reps, you are asking the large language model to represent your text using only one word, but you can extend these and say, oh, no, use 2 words or 3 words, right? Or you can extend these by saying, okay, yes, I tell you to generate multiple words, and then I don't use just the last word, the last token, and I get the logics associated to that, and the lastly, the layers associated to that. I actually look at the generated words. I take their logics for each of them, their logics and their embedding, and I do a Colbert style type of modeling and representation. So I use multiple tokens, not just one token. There are a bit of trickeries there around the fact that, unfortunately, a word in natural language is not a word in these language models. So, you know, a word in natural language can be multiple tokens. And so there's a bit of work to be done there on how you deal with these multiple tokens for a single word. But the approaches do work. These multi-word, multi-document approaches don't work better of that one single word, surprisingly, but they still work decently. Okay, so that's a very quick overview of how we could use these LLMs as creators or representations for doing retrieval. And next, I want to talk about how we can use these LLMs for ranking. So here the plan is that I will talk about, at a very high level, about 4 families of LLM-based rankers. And then I would talk about prompt variations. So these LLM rankers work on you writing a prompt to instruct them how they should rank things. And so we look at how variation of that prompt, what variation of that prompt generate or matter. And then we will talk about prompt optimization. Very behind in terms of time. Good. So the idea here is that we have a query and we have one document and multiple documents. We put them together along with some instruction. We put it in the prompt. We pass the prompt to LLM. We get a ranking out of that. Okay. All of these methods are zero shot again, right? Once you have obtained the model, right? Once you have downloaded the model from Hugging Face, that's it. You don't need to do any further training there. So I told you there are 4 families. The first family is a pointwise ranking. That means that you give the query and one passage, you put into your prompt, and then you ask the LLM for whether the passage is relevant or not, or you ask the LLM how relevant that passage is. And so for these, you would use typically the logics of what the LLM generate. Different approach does a query likelihood model style, but it's still pointwise. You give it the passage and you ask it to generate the query for that passage. And so what you get is a distribution out of your vocabulary, a distribution probability out of your vocabulary, and use that as a query likelihood model. But the idea is you pass the query, you pass one passage, you get a score. You do it for every document you need to rank, and then you order them according to that score you get out. The listwise methods, what you do instead is you give the query and you give a list of passages. So that's an ordered set of passages. And you ask it to generate an ordering of that list according to relevance. Put the first document ID rank, first, the most relevant document ID first, and then the second one, and so on. Okay? So you generate a list. And the third method is pairwise. So it's a simplification of that listwise approach. You give the query, you give 2 documents, and you ask which one do you prefer, which one is more relevant between these 2 documents. And you do that for all possible pairs, or a subsample of the possible pairs that you have of documents to rank, and then you induce a global ranking out of that. And finally, the 4th family is the setwise method, where you similar to listwise, you give multiple documents in input to your LLM together with the query, but you treat them as a set, not as a list. And then you get the model to generate the ranking, and you use the logics to sort the list they generate. I'm going to skip the rest because we don't have time, but there are some more details on how you do the sorting in setwise, how you can use some of these trickeries in setwise and reapply them to the previous families to make them better. And then a bit of a consideration of trade-off between, that is what I'm showing here, trade-off between effectiveness and cost, so number of computation inference that you do. Okay. I'm going to skip through the problems of listwise and methods that have addressed those. We do not have time. In short, the problem you have with listwise is that the context or the prompt size of your LLM is limited. And you have heard it a few times today and previous days. But you might have longer, once you put your passages together that you need to rank, you might exceed the size of your context, the size of your prompt. And so you start slicing that list and do your listwise approach multiple times and then try to aggregate those. And this means you're doing this, this approach start becoming inefficient. And also there are other problems around the generation of the doc IDs. Sometimes these models don't actually generate correct doc IDs, so you need to rerun that a few times. So it's not great. And there have been methods for listwise rankers where instead of taking the text of the passage, they take an embedding of the passage, they put it into the prompt, and they use that as a way to fit more things into the prompt. And so that an example of that is PRank. I'm not going to talk more about that because we talk about passage compression in RAG if we have time. So let me skip next. The thing that it should be obvious to you once if you saw this little prompt that I showed to you is that these prompts differ not just by the algorithm for ranking that they say the language model to use, but also by other type of wordings. That's what are spurious wording. So look at this example. You have PRP, that's a pointwise method, and the prompt is passage query, does the passage answer the query? And then you have rank GPT, so that's a listwise method, where you start having a lot of other accessory wording. You have role playing going on there, right? You are an intelligent assistant, right? You have restriction around the format of your answer. You have restriction around the formatting, how you should format your answer, and what you should output, like you shouldn't output an explanation and things like that. And you look at the other prompts that have been devised for other methods, and you see more and more of these, right? And you know from using ChatGPT how the quality of the answer you get out does depend on what you write in that prompt. Right? You might have the same information need, but you express it in a different way, you get different results. And so how does these changes you can do to your prompt, how do these changes affect the quality of these rankers? So here is a study where there have been something like 25,000 different experiments run with different variations of prompts, where you have role-playing, you even go and insult the model or be very nice to the model, and see how that influences your retrieval, your ranking, sorry, in these 4 large families. And what you start observing is that there are some families that are really robust to prompt variations, so that's your pairwise and your setwise methods. And there are some families that instead are way less robust. Pointwise is usually very unrobust, right? So you're lucky. You need to open to be lucky, right? I'm not going more into that, but I invite you to look at that paper, look at the slide, look at the paper. And so that should make you immediately think about, okay, if I can go there and slightly change the prompt manually, why don't I come up with methods that can change my prompt automatically to try to figure out automatically at a large scale the best wording I can use to construct these rankings, right? So this is what automatic prompt engineering attempts to do. So here is a method for automatic prompt engineering that is a PR that again, I do not have the time to explain it in detail, but what it does is it generates variations of the prompt, and it tries to use feedback that it creates itself, that the model creates itself, to estimate how good the prompt is, and therefore to guide the new generation of prompt, right? So do it iteratively using a reinforcement learning type of approach. Okay. Let me skip here. Okay, last few minutes, I tried to cover the next 2 parts. Not too much. Okay, the second part is retrieval augmented generation. Now, we are lucky because Suzanne already showed you the typical pipeline for retrieval augmented generation, right? You have your external knowledge, right? Your document collection, your index, you have your query, you send it to a retriever, the retriever finds the top K document, you put that top K document into a prompt, you send that prompt to a frozen large language model, you get your output. That's the retrieval augmented pipeline. Now, why doing RAG? Again, you heard it. These LLMs do have a lot of knowledge, but this knowledge is limited. Then not up to date to yesterday if you train the language model to a year ago. And then, yes, hallucination as well. And so the solution is to use these external data sets in order to incorporate new information or to refine the capabilities to kind of reduce the hallucination of these large language models. And you have 2 ways to do that. One is RAG, the other is unsupervised fine-tuning, right? You have trained a large language model, now you get new data, and you go and you use that new data to refine your language model in an unsupervised way. And there is a work from Microsoft that shows that clearly RAG is superior to unsupervised fine-tuning, and therefore it's, let's say, the right way to go, the more promising way to go. Okay, so we say this is the pipeline for RAG. You can actually extend a bit more this pipeline for RAG to really, to do more, to use all the work we have done in information retrieval for the last 60 years to try to improve search, right? And embed it into your RAG pipeline. So you can do pre-retrieval tasks. Before you send your query to the search engine, you can do things like query writing or query expansion or even query routing. If you think about, if you are a large enterprise, you do not have just one index. You have many information systems. You have the HR, if you're a university, you have HR that has their own data, their own website, their own knowledge bases. You have the library that has other, you have your own department that has their own information system and knowledge. A different department has their own. And so you might want to do query routing there. Once you get a query, you want to understand where you want to send your query among your multiple search engines. But then you can do things post-retrieval as well, right? You have done retrieval, you can do further re-ranking, so further refinement to these. You can do some things like summarizing multiple documents that have gone, you summarize them into shorter things to then pass into your prompt to deal, for example, with context limits of your frozen LLM. And similarly, you can do some type of prompt compression in other way, and so on. And that has led people recently to look at this idea of a modular RAG pipeline, where you have these different components which you can actually assemble into different patterns. So the figure shows you up there, shows you possible components that you have in your tool library. And at the bottom, you have different patterns of how you could assemble these components together, and how that give rise to different styles of doing RAG. And what that, seeing RAG in this way allow you not just to come up with different methods for RAG, like different pipelines, but actually allow you to do RAG in an adaptive way. So you could say, hey, given this query, given this request, I should use these components of my RAG pipeline, but given these other requests, I shouldn't use these components. I should use maybe a more lightweight component, which the query is easier, or a more complex component because the query is more difficult. As an example of that, or maybe I shouldn't retrieve at all, actually. I should rely on the model parameter. And so an example of that adaptive pipeline is self-RAG. Good. So what I wanted, what the slides talk about more in depth is methods for doing RAG. So some examples of these pipelines that I talked about, methods for doing prompt compression, because now you are retrieving the passages, you are trying to put them into your prompt size is fixed and is short. How do you put things inside there if you have more things to put in than what your size limit is? So you want to try to compress that. I wanted to talk about the struggle between the evidence you get at retrieval and the evidence your model has learned and has encoded in that parameters. I wanted to talk about attribution. So the fact that you are not interested only to generate an answer, you're also interested to ground that answer on evidence you retrieve and to tell the user that you generated the answer because here is the origin information, here is the origin information, here is the origin information. So you want to cite. And then I wanted to talk about resources and platform for RAG. So let me skip through the different methods for RAG. Let me, and also I skip through prompt compression. You can have a bit of a read there. I want to talk about the struggle between retrieval and LLMs for a few minutes. because I found it quite interesting because we actually haven't figured it out at all. So the output of your RAG system, you have no formal guarantee that is consistent with the information that you have retrieved and that you have passed to the LLM, right? So you have no theoretical guarantee that given these passages input, the answer is based on the passages. Okay? And that's because that's for a number of reasons. One of these reasons, the most basic one, is because the models these LLMs have not been explicitly trained to leverage and to follow the facts from your retrieval pipeline, right? Here an example, a study that shows example of answers inconsistency in a RAG pipeline. So say that you ask ChatGPT the question, some questions like, will drinking vinegar dissolve a stuck bone? And you ask the LLM to say yes or no. So we ran this scale. We got these sizes of answers. This is our ground truth. We ran this scale. We got data with ground truth with these questions, and about 40% of the data we had had answers yes, and the 60s answered no. We send it to ChatGPT, and ChatGPT, you see, does quite well. 80% of the time give you a correct answer. It does fail from time to time. It has a tendency to tell you that yes, an answer is yes, more incorrectly than telling you that an answer is no. But that's okay. So bias there. And now you say, no problem. We know that LLMs hallucinate. The solution is RAG. Let's do RAG. Let's take the questions, send the question to our retrieval engine, retrieve some evidence. For example, your top one passage, pass that evidence to ChatGPT, tell ChatGPT they should base the answer on that evidence, and then go, right? And so for this study, we did something a bit smarter. We actually went and we didn't use our retriever, right? We didn't use our pipeline. We said, let's control the passage we give. We know which passages contain correct information, which passages contain incorrect information. Let's see how this plays out. So in particular, we had passages that have supporting evidence, so passages that provide the same answer as the ground truth, and passages that provide contrary evidence, passages that provide an answer that is different, goes against the ground truth. So when you do that, you take your correct, so you take your questions, you send them to the RAG pipeline with supporting evidence, and you send them to the RAG pipeline with contrary evidence. You do this for both correct and incorrect questions. What you would like to see is that, starting from the top, if the model answered incorrectly before, and now you're giving supporting evidence, the model should change their mind and should give you the correct answer. If the model answered incorrectly before, you give incorrect answers, you wouldn't expect any improvement there, right? If I'm giving wrong things to the model, it shouldn't improve at all. And when the model was correct before, you expect to see that if you provide again correct evidence to the model shouldn't change their mind. It should still be correct. And when you give incorrect answer, you're hoping for the best. You will reach the model, doesn't change mind now, but you know that you will have to pay the price, that the model will change mind, right? Otherwise, you have no consistency there in model behavior. But then when you actually do that at scale and you measure what's happening, you start finding weird things, right? You start finding that if you provide supportive evidence to try to overturn an incorrect answer, that doesn't flip the answer, right? The answer is still incorrect, but I give the correct answer in RAG, right? Wasn't RAG supposed to fix hallucination? Yeah, no, not really. And then you even find that I provide evidence to the model, and by providing evidence, I flip a previously correct answer in a no-RAG pipeline to now an incorrect answer, right? That was when I was giving something correct in my prompt, or when I was giving something incorrect in my prompt, it doesn't matter. I still can flip something the model was correct before to say no, an incorrect answer. Right? So this shows how we haven't really understood how we can control this interplay between the knowledge the model has and the knowledge we pass in the prompt in order to really exploit the RAG pipeline. And there is a similar study that is going to appear in a couple of weeks at ESSIR, where they show some other type of weird behaviors related to the relevance of the passages you give, so similar like before, but even the positions of the passages you give in the evidence list that you give in RAG, and in particular, let me skip to their funding. In particular, they find that if you provide the correct evidence in the top, you get good answer out. If you provide at the bottom of your prompt, you get okay answer out. Rather in the middle of the prompt, that's it. It's not working anymore. The model doesn't listen to evidence that is there in the middle, right? And so you have that lost in the middle effect. And they even looked at when you don't provide a correct answer, what happened to so when you don't provide a correct passage, you provide a related but not relevant passage, or you provide a random passage. What's happening? And what they find out is that if you provide a random passage, you actually improve the quality of the generation than if you provide a related but not relevant passage. So again, type of surprising behaviors that make you wonder, how are we going to really control these RAG pipelines? So there have been since methods that have tried to improve this situation, for example, by trying to get these large language models in a RAG pipeline to pay attention to the middle level of the prompt. And in the slide, you can find an example of that method. Again, I'm not going through it, unfortunately. I'm not going to talk about attribution for interest of time. I'm talking let me talk a minute about resources and platforms for RAG. There are many platforms that are starting to emerge in this context. And there are some industrial-oriented platforms like Llama Index and LangChain. There are even platforms that are provided as a service. And then there are research-oriented platforms that are also emerging. And if you want to do work in this area, you will struggle to decide which way you want to go, right? If you are, the research-oriented platforms give you a lot of benefit to, for paper writing, because you have a lot of baselines and comparative methods and even corpus reading tools already integrated in there. Your industrial level platform will give you the advantage of be able to very quickly translate the research you do into actual commercial product, or at least commercial uptake. There are also resources in terms of data sets. There are many data sets available that people are using for RAG, but they are actually not necessarily focused on RAG. And so there are issues in using these data sets on RAG from a number of aspects, from the data characteristic to the actual evaluation measures that are used for those data sets. But there are a few recent data sets that are emerging. And one of them is the RAG track for this year, which is going to close on the 11th of August. So if you do RAG, you should participate. You still have about a month to work on them. In the slide, you can find a couple of examples of these resources, particularly Bergen that just has come out 1st of July. And if you want to talk more about Bergen, I think Timbult is somewhere around here. I don't see him. But there is one person here that was formerly, there's a PhD student here in Amsterdam that was formerly at another lab, and he has helped creating this resource. So chase him up. And then you can also find a bit more details about Track and Runnerrock, that is the platform that the track organizing are providing to facilitate your work if you're participating in track. And very weird the name for the platform. Go on the slide and have fun. Okay, so there are many open directions in RAG research that not that I didn't talk about, I didn't have enough time, but that I even didn't touch upon the slides, right? And so there is a very good survey I want to point you out to, that is there at the bottom of the slide, where not all, but many of these questions are actually looked at, and they provide you a very good overview of these. So please do follow the link if you are interested in RAG. Okay, I'm already over time, but I'm going to tell you two things about model-based IR, and then I'm going to try to conclude on a high note. Okay, so I just give you the gist of model-based IR. Our traditional IR pipeline is that we have a query, we have an index, whether it's a sparse index, a dense index is an index, and then we do somewhat a retrieval stage, we do somewhat a ranker stage, we get a result. That's what we have always been doing, right? That's what we have seen so far. The idea of model-based IR is that now get rid of your index, get rid of your retriever, get rid of your ranker, just take a pre-trained model and use that pre-trained model to do the whole task, right? What you just want is that the pre-trained model has encoded in its training process, has encoded all the corpus on which you want to do that retrieval, right? And so that's the whole idea of creating a unified retrieval rank framework, and that's the idea of the ESSIR. And the advantage there is that you then have a model that can answer a whole sort of different tasks, and it will scale very well because suddenly you don't have an index that keep exploding as more documents put in. You just have this fixed parameter size model plus some additional data structure. Okay, let me skip here. So why you want to do what the ESSIR does? So why do you want to get rid of all these pipeline and try to learn a model that, yeah?
Just to be sure, you still have half hour.
I do? Ooh. Ooh. Sorry, I thought we were finishing at 12. Yay. Let me go back then. Now, so I go back to RAG, but before going back to RAG, let me finish the ESSIR since we are on it. Ooh, thank you, Mohammed. Embarrassing, but it's good. I'm happy. Okay, so I told you about we have this unique model that is trying to learn your corpus. So the idea here is that you want to jointly learn the task of indexing and the task of retrieving. And you do that by optimizing a loss function that relates to your indexing task, or your presentation task, and a loss function that instead relates to how you retrieve documents for a query. And what the model does is it takes queries, it takes documents, you get them at indexing time, it takes query and it learns, it changes the model, delete. It takes documents and it changes the model weights. And then at retrieval time, it takes the query and it outputs document IDs, right? So those document IDs that you pass together with the text at indexing time. Why you want to do these type of models, right? Why you want to do these DSI models? There are a number of reasons. One is an efficiency reason, an efficiency at inference reason, not efficiency at training, unfortunately, but at inference. So you have lower memory utilization for this model than in traditional retrieval pipelines. Your inverted index in a traditional retrieval pipeline grows as your corpus grows, right? Instead, and that's the same for a dense index, by the way, right? If your corpus is 1 million and 1 million documents, you have a dense index of 1 million embeddings. If now your corpus is 2 million documents, you have a dense index of 2 million embeddings, right? So you are growing that index. But instead, with models like the ESSIR, your model doesn't grow. The model is fixed in terms of the number of parameters, right? So it's highly scalable. There is some small amount of overhead I mentioned before because of your doc.id storage. That's a little trickery to do to make sure then you can constrain your generation of document ID to a set vocabulary of document ID and not to get errors in your generation there. The other advantage in terms of efficiency at inference is the latency. You have latency improvements. Your generation is quite lightweight, and so you get very fast retrieval. But there is another advantage of using these model-based type of retrievers, that is that you are dramatically simplifying your information retrieval system, right? You are throwing away indexing, you're throwing away you're throwing away retrieval, you're throwing away even the generation process. If you were thinking about a RAG pipeline, right? You're throwing away your pre-retrieval estimates, your post-retrieval re-ranking and stuff like that. You're substituting this stuff with one unique thing. And that means that you have less engineering to do, you have less maintenance to do. If in a traditional system, if somebody changes your query processor, then you don't know the downstream effect on your retriever, for example, and your ranker, and then you need to scramble around to try to see the implication. Here instead, you don't have these components that need maintenance and need so maybe that's not an architecture maybe Google cares about. They have a lot of software engineers to do engineering and maintenance. But if you're running a small e-commerce website, for example, it's a big burden having to deal with all these different components that interact and that updates by third parties, and you don't know how that update downstream in the task. If instead you have just one thing, that's much easier. Okay, and there is another simplification there. If you think about RAG, right, you have even more complex pipeline than a standard retrieval. But imagine if these ESSIR models don't just generate doc.IDs, right, as they currently do, but also generate actually an answer with doc.IDs to grant the transfer, right? Then you don't really need RAG, right? You can substitute RAG with these type of models. And there is a paper at CIR this year that actually does this. So it's a good paper. I forgot the title. It's a good paper to look at. Okay, let me backtrack then a minute, since we have time. Let me backtrack to RAG. And let me, get in there. Let me do like this. So we have 20 minutes. I want to say 5 minutes at the end for something, for a bonus. We have in RAG, we have a few components or a few different areas that I prepare material for. Can we do a show of hands of what you care most here? So for example, who cares about prompt compression? Anybody knows what prompt compression means? Yeah, one knows, okay? Yeah, 2 knows. So again, let me repeat, I mentioned it too fast before. You perfectly know that these large language models have a limited context size, a limited size in the prompt, right? For example, who remembers how many tokens can you input into models like Llama 2 and Mistral? Sorry? 4096 for 4092, maybe, or 4996, yeah, something like that, for 1,000, right? What happens if when you create your prompt, you have more than 4,000 tokens? That's because you have your instruction, and then you start appending passages to your prompt, and these passages you have retrieved very long. What happened there? Right? You don't want to do truncation of your prompt and lose some of the passages or lose some of the information in the passages. That's bad, right? That might be bad. So ideally what you would like to do is you want to reduce your prompt from something big that exceeds your context into something smaller, right? That's what prompt compression does. So now that you know about prompt compression, 1, 2, 3, maybe 3, okay, 4, good. What about attribution? Who remembers what attribution is? Yeah, you all remember? Who cares about attribution? Oh, that's the same, a bit more from compression. What about methods for RAG? Who cares about different pipelines to do RAG? Different methods for RAG. Yeah, more people. And what about, we talk about the struggle. So, okay, let's go through methods for RAG then, since it was more or less the majority of the people. Sorry for the pre-compression girls. A few methods that I highlight. The first method is called rewrite, retrieve, read. And it is quite simple to understand. The idea here, and you know how before I told you that you can look at this RAG as putting together different components, right? This is a clear example of that, right? You have one component that is tasked to get the query of the user and rewrite it into another query, a more effective query, hopefully. So that's the rewrite block. Then you have one block that is tasked to do the actual retrieval, so the search with that rewritten query. And you have a third block, the read block, that given some instruction, given the query, and given the document, now generate the answer. Okay, so let's have a look at how that actually end up being implemented. So the rewrite block is it's often done with some few shots in context learning. So you provide a prompt with the instruction to rewrite the query, few demonstration of effective query rewriting, and then it gives you the new query that you should now rewrite. And the output can be nothing. So now I wasn't able to rewrite a query, or it can be one query, or it can be even multiple queries. And so if you have no query, you just go on with your original. If you have a rewritten query, then you do something with that rewritten query. If you have multiple rewritten queries, you might fork out multiple searches. So you will have that retrieve might be instantiated a few times to fork out that and serve and then fuse in the read. So here are some examples of how these instructions that you give to do the query rewriting look like. An example for the open domain question answering, you see that people like to use these weird approaches to make your prompt better, like think step by step. So this is chain of thought strategy, right? Other people will say, take a deep breath and so on. Apparently they improve the quality. And, but you see here, you get a little instruction, you get some demonstration, then you give your original query and you get out some answers. What you could do to improve this idea of rewriting queries is to actually training that rewriting, right? So you can do it zero shot, or you can go and train a rewriter. So you can train the rewriter in the example here from ENLP. You can train that rewriter with a warm-up task where you use some pseudo data. So you can you can go create some query and then try to evaluate the query and only keep queries that led to good results, and then use these to fine-tune your model. Okay, the next method, example method of RAG pipelines is a blend filter. That is a recent method. And here again, they work on this idea of the query writer, right? By enhancing input queries through different augmentation strategies. So you see the query generation block up there. It has the initial query, that's the original query, and then it has two different strategies to enhance queries. So let's look at the two different strategies. One is to use the external knowledge to improve your query. So there you take your initial query, you send it to a knowledge base, for example, Wikipedia. You retrieve passages from Wikipedia. You take these passages and the query, you send it to your large language model, and you ask the large language model to generate queries related to the topic of the query, but for these passages, right? And this way you get this query rewriting. And then you can alternatively even generate for those queries, generate answers, use these answers as concatenation to your query. And then there is another way to augment your query. Instead of relying on the external corpus, you can rely on the weight of the model, so on the model itself. And so instead of taking the original query, send it to a retriever and get data out and generate an answer, you ask the large language model directly to generate an answer. So then you could use, for example, a more complex language model that you are using and use this as a sort of distillation method. Right? And then again, you take the answer generated by the large language model, you concatenate to your original query, and now you have a larger, an expanded knowledge that you're passing to the next step. And in the next step, then you can start introducing another module that is knowledge filtering. Okay, you know, now I had my query and my original query. I can get the LLM to answer my original query. I have my expanded query and knowledge through an external repository or through a different LLM that generated those answers. I can use these to filter out some of these answers that have been generated, okay? And put all these together. So try to, for example, filter out things that are contrary between each other, right? Put all this together, send it finally to my LLM to do the final answer generation, okay? And so here again, you will see an example of that. And so the LLM finally will generate that answer based on the filter and knowledge and what the original query was. Yep, we still have a bit of time. So the last method I wanted to talk about with respect to RAG pipelines is something that to me is very promising in terms of making, you know, breaking away from a fixed mindset of how we pipeline these models, and instead looking at more adaptive architecture for RAG that allow us to answer differently to different queries. And also that means that we could have a more efficient and effective generation answer. So an example of this adaptive way is the retrieve, generate, critique pipeline, or called self-RAG. And what self-RAG does is, given a query, it has two decision points. One is whether it should issue the query to a retriever or not, so whether it should retrieve, or it should instead directly generate an answer based on the model parameters, so the knowledge of the LLM. And then it has another decision point that is, if it has issued a query, it has retrieved passages, then it would go and reflect on these data. And so it could reflect on the answer that it generates, right? So you know, it will critique the answer, and if the critic of the answer say, yep, the answer is good, that's the answer you should to the user. If the critic of the answer is that says no, the answer is not good, then it goes back and it redoes the search based on that. So you see these more adaptive type of approaches. Okay, now because there were a few more people interested in prompt compression, I try to very quickly go to prompt compression before we skip forward at the end. So prompt compression, I already told you what it is, and why it's important is because of that long prompt you cannot fit into your prompt. There are another two motivations. One is that often long prompts confuse your large language model and lead to low effectiveness. That's the case if you think back when I very quickly talk about this new ESSIR paper coming out where they found that information that you put in the middle of the prompt get lost, right? The model is not paying attention to those, right? And that's a good example of when your prompt is long, that then you start having these sort of effects. But also there is another issue with the long prompt, and is that I think it was in the opening, in the first few slides of Suzanne, is that the latency of this decoder-based LLM is quadratic with respect to the prompt length. Now you can do smart things to reduce this. You can do a prefix, for example, computation of your prompt. But in most cases, in some cases, especially in RAG, that might not be possible. And so if your latency is quadratic, the longer the prompt, the longer and longer it will take to generate an answer. So people have come up with two high-level categories of methods for prompt compression. One is lexical-based prompt compression. That means that you have your original prompt, and what you want to do is you want to decide which words out of that original prompt you're going to dump, right? So it's almost like you're creating a little summary of that original prompt. And another family of methods are embedding-based methods. And there is, instead of using the actual text of your passages to put into the prompt, you use an embedding of your passages, and so you put the embedding into your prompt. And you do this through adding some special tokens to your LLM vocabulary, and using these special tokens, that are your memory tokens, to have those embedding of your passages. Okay, prompt compression, lexical-based prompt compression, let me skip them. They're pretty easy, pretty obvious. You can do some smart things like this one in the slide. Probably it's one of the slightly more sophisticated methods for doing lexical-based prompt compression. I think it's the Lingua 2, LLM Lingua 2 method, but they're still quite simple. Let me instead talk about these embedding-based prompt compression method. And I'm using the ICIE method as an example. So the idea here is that we want to compress part of the prompt into a special token, so these memory slots. Then we can use to then condition the LLM to generate, to do the generation, right? And so if we are introducing some new tokens, by introducing new tokens, we are introducing new parameters, right, into the model, which doesn't sound like a great idea, right? We are making the model take longer because we are putting more parameters. But in reality, by just introduce 1% more parameters, we can get a 4x prompt compression. So we can reduce massively our prompt. And that means that ultimately we reduce latency, we reduce GPU memory cost at inference. So here is how this is done by ICAE. You use your LLM as an encoder model to compress your original context and the memory and some special tokens into these memory slots, right? So you have introduced some new token to your original context, and you are looking at the embeddings of these new tokens. And then that's what you do in the encoding phase. And then in the decoding phase, you don't pass all the tokens that you pass to the encoder. In particular, you don't pass your original context, your original prompt. You pass only the memory slot. You only pass the embeddings of the memory slot to your decoder, and you get that to do the decoding. Additionally, you do still put some additional instruction along with your memory slot. So you haven't embedded all your prompt into the memory slot. You are only embed your evidence, your passages in there. And obviously, you need to train this, right? You cannot do it out of the box. You need to train now this new model so that you train the representation of the memory slots. Okay. So as an example, right, you can get passages to put into your original tokens. I forgot to put the number of tokens that we originally have. Say that we had, actually, we had 128 tokens in our context. We want to compress that into 32 tokens. Doesn't sound right. No, 128 tokens is the memory slot. We have way more token in our context. So I think it's 32 by 128 is how many tokens we have in our context. We want to compress that in our, we want to compress 32 by 128 into 128 tokens that are our memory slot. We want to send those 128 tokens to our decoder. We add a bit more instructions. That's the prompt there, 12 more tokens. And what we end up doing is, there it was, we end up compressing a prompt of 4,000 characters into 4,000 tokens into a prompt of 140 tokens. So it's huge saving there. And so we can be faster. We can put more content into our prompt. Okay. That's all. I'm done going to the training procedure. That's fine. Let me use the last few minutes to kind of move out a second from this detailed, more detailed view of generative IR and talk about something that has come out recently that to me is very similar, very related to that model-based IR, but is taking the idea of model-based IR to the extreme. Right? So it's extreme model-based IR. And this is a paper from DeepMind of a couple of weeks ago. With a very weird title, if you ask me, right? When I read the title, I was like, oh, this is very pretentious. So the idea is this. The idea is get rid of your IR model with your index and your retriever. Get even rid of your DSI type of model where you only have your model parameters, but you need to train these model parameters, right, to encode your corpus. Just take one of these LLM and put all your corpus, all your collection into the prompt, and go ask that model to do retrieval or to do answer generation or to do whatever other task you want to do. Now, right, so to make it clear, right, your what you're saying is that you take this large language model, you write a prompt like this, where you give some instruction, then you put all your corpus in there. Right? Imagine you take MS Marker, you put it all into your prompt, and then you provide some example of the task you want to do, so some example of your retrieval task, some example of your generation task, and then you give your new the query formatting. You give your new query, you format in a particular way, and you say, okay, now do retrieval for me from those documents that pass in the prompt. And now, if I don't know you, but when I saw these, I was puzzled, right? I'm like, oh, come on, that doesn't sound like a good idea. If I need to be honest, right, I actually thought these people are idiots, right? And I mean, this is because, think about it, right? Oh, come on, how can I fit all my collection into the prompt, right? And then you're like, well, yes, but there are these new language models are coming out that are having bigger and bigger context. Like, we say Mistral has 4,000 tokens. We look at Gemini 1.5, it has 1 million tokens. Yeah, okay, I see how if my collection is not web scale, right, it's my e-commerce, small e-commerce website, yeah, I could actually fit everything into 1 million tokens, no problem, right? And yeah, maybe, we went from 4,000 token to 1 million token in 6 months. Yeah, maybe, in next year we are at 1 billion token. Yeah, okay. Maybe fitting all the documents into your prompt can be done, but it's still a bad idea. I mean, maybe you're a slightly idiot. It sounds like a bad idea because this is going to be so expensive, right? We just said, Suzanne told us again, right? The computation is quadratic to the size of the prompt. So if we are putting this huge amount of corpus inside our prompt, they're going to take forever. So here is from their paper, right? Them telling you, yes. So we ran our experiments. We had 448 million input tokens, right, throughout all our experiments. That costed us, we used the APIs, it costed us $1,500 for Gemini or $6,000 for Claude, right? And in particular, it took us 100 seconds to do an inference for each query, right? So forever, right? Doesn't sound good. The cost, not too much of a problem, in the sense that if you have your own language model that you are serving yourself, not too much of a problem, and the API cost will go down anyway. But is that time cost that I thought that's a bad idea? But then, then I thought, hang on a second, maybe I am the idiot here, right? Because you can reduce your latency quite substantially by doing prefix caching, in the sense that ahead of time, what your collection is, right? And that doesn't change from query to query. It's always the same collection if you're building a search engine for a particular company, right? Sometimes each agency will do some updates to your prompt, but today you have that fixed. So what you can do all these all these things, you can pass it into your LLM ahead of time, cache, all that, and only at runtime online, you only pass your new content, so your query, right? So that reduces your latency massively, right? And then I thought, given the speed of research, maybe soon we will come up with even more efficient methods to do that latency inference. So maybe this is not that crazy idea. And then thinking a bit more, I think there is more of why this actually might be a very good idea. So think again, right? Compared to RAG, you have the same advantage. This architecture gives you the same advantages of the ESSIR, right? You have no multiple components, you have no frameworks, you don't need to maintain different things, you don't need to train different things. You don't need to run different things. Right? Very simple things to maintain. And then there is an advantage compared to the ESSIR. These are requests not training, right? You're giving only those few examples, those few demonstrations in your prompt, not training required. While in DSI, you need to do a massive amount of training, cost quite a lot. And so, you know, all this is done zero shot. So actually, this is a great idea if it works. It's a great idea. So I wanted to conclude on this one because I think is a method that has just come out. If you look at the paper, it's not super detailed. Nobody has reproduced it yet. Who knows if it really works and so on. But actually, it's very promising. And it's showing us something. It's breaking away from our traditional view of information retrieval, right? And so, you know, these make me reflecting on the fact that there are many promising directions on how we can use these large language models to empower search. And these models can really create some radical changes to our retrieval pattern, how we see our retrieval pattern, right? You know, how we see IR, the field, and how we create search engines. And in particular, Suzanne mentioned it before, right? Of this view of IR, and if you go to that BAI conference, the Chinese conference, you will hear it a few times as well. The same thing that says, "Oh, IR is dead. IR is not good," because what IR is document retrieval, right? That's what you will hear, and Suzanne said it as well, right? And what I want to tell you in this last slide is that I think this large language model and this generative IR is giving us the opportunity to break away from this 60-year-old view of what IR is, being document retrieval, right? We inherited from Lancaster in '68, right? Move away from these and think that information retrieval is not document retrieval, it's actually information, right? And is how we provide access to our users to information. And if you go back to library science, that is where IR comes from, right? Evangelos told you the first IR system was a library, the inverted index and so on. Well, in a library, you do information retrieval in two ways. One is you go to the index of the catalog and you find the book and you get the book, right? And that's what we have been doing until now, our inverted index. But there's another style of information retrieval that you do in the library, well, that you did in the library 60 years ago, you don't do it anymore. That is, you go and you talk to the person, you say, this is my question, and they have the knowledge to answer that. They have the knowledge because they are expert and they can tell you that, or they have the knowledge because they've gone and read documents, so they've done, let's say, the retrieval augmented pipeline, or they go and find somebody else that is expert and can answer that. So there was an event about a year ago in Melbourne, organized by Mark Sanderson, where he was showing the advertisement of the Sheffield Library Services in 1960s. And we were seeing exactly this different style of information retrieval, where there wasn't just this funding a book, but there was this providing information to the user, right? And so I believe that there is no better time to do information retrieval now, and for you that are young, that haven't been biased by this view of what IR is, to actually take the field, embrace these generative models, and try to change the way we provide access to information to users. That's it, only 10 minutes over time. Thank you so much.